That wonderful time of the month again, the UQCCR seminar series, and we've got a couple of fantastic presenters again this time round. So we have Paul Colditz, who we all know very well, head of the Perinatal Research Centre, and a long-time strong contributor to so many of our careers here at UQCCR, will be providing the first presentation. And then secondly, we have my namesake, Jay Roberts, but more accurately, Associate Professor James Roberts from QIMR Berghofer, who's going to follow on thereafter. So I might invite Paul to come up and present first, and then we'll invite James to present thereafter.
Thank you very much, Jason, for the introduction. And I'm actually only the front runner for a collaborator from QIMRB that I'll introduce when we get to his part of the talk. So mine's quite a short intro, and you might be thinking, hang on, I've brought along the wrong slides, because you'll see up there, Australasian Brain Club inaugural meeting. And when my own kind of postdoc says, Paul, you've got to talk, what can I do other than obey Julie Wixie, who organises this series? And I thought, I'll use this as a starting point to really introduce the second part of the talk. And this was something I didn't have as much control over as I might normally be able to exert. So there were some topics that were offered as TBA, to be announced, but mine was AEG, are we missing important prognostic information? And so I thought I'd better follow instructions again and stick to topic, because most of my experience and interest in EEG has been around characterising sort of fine details, using signal processing approaches, and particularly around seizure detection. So this AEEG, what particularly is it? And look, it also bears the name CFM, Cerebral Function Monitor. It goes back to the 1960s. So just on the cusp of electronics being implemented in old-fashioned valves and so on, as opposed to modern microelectronics. So a lot of they were thinking in those ways. And so what you could actually do versus what we need to be doing were quite different things. But then as we've got new microelectronics, how did we implement it? So I've just taken this from it's a key paper referred to in many studies, as this is how we define AEG and how we use it. And from their paper, and this includes literally all the senior players in the world, it's an asymmetric bandpass filter of Aurora EEG that attenuates below 2 Hertz. Now, that was a kind of hardware limitation at the time. And we know so much power, unlike in adult EEG. In the neonate, there's a lot of power in the EEG and significance below 2 Hertz. And we throw out a lot of high frequency part of the signal as well, that you certainly wouldn't particularly necessarily want to be doing in adult. So how people have implemented that across time is quite different. There's, again, some semi-logarithmic amplitude compression, rectification, which sort of flips the negative and positive signal into a positive direction, and can be done in a number of ways, smoothing a number of ways. And then the real kind of opportunity to be realised was if we compress it, so in time, and just look for patterns, that's where we're going to get the mileage out of this AEG. So it's manipulated different ways, different occasions, but it does result in this thing that you can see is a solid block. So on the top right there is a pretty normal AEG over probably a couple of hours. I can't see the scale there myself. And you'll see as you move down the page, perhaps to this panel here, that it's looking different, certainly, and it's got a low voltage with multiple repetitive spikes through to the final panel there, which is very little EEG activity whatsoever. So you can see that pattern recognition and seizures, I should say, I haven't shown a pattern here because it wasn't really part of what I was asked to talk about, has a characteristic chunk out of the bottom line there. So it doesn't look like EEG anymore, but people have taken the use of this functional measure of brain activity to simplify it and try and make meaning. And indeed, it has sort of received meaning in a number of ways. So people probably be familiar that in neuroscience, one of the very few indications for hypothermia to treat brain disorder is in the neonate. So, and babies were recruited into these studies, which were all done about a decade ago, on the basis in part of what their cerebral function monitor or AEG pattern looked like. And there are these three basic things: a background pattern, sleep-wake cycling, which is as simple as present or absent. If it's there, it's good. And seizures, which, as I've said, are reasonably characteristic pattern. But if we look at the background, because that's what I was asked to deal with, and I've just blown that up there, you've really got like 1, 2, 3, 4, 5 patterns. And from this, we're trying to infer something about outcome, because at the end of the day, so much about what we do in neonatology, where we're trying to make interventions, where we're using treatments, or indeed we've got this baby in this very alien environment relative to the womb. Could our standard care actually be sort of modifying brain development? So again, sticking on background EEG features, these are a couple of PhD students' papers where part of their PhD was to say, before we set off in a refined way looking at background EEG features that we ought to be pursuing in a new research sense, what's the literature tell us? Conclusions, and this is after many years of research around the world. There's preliminary evidence that background EEG features can predict cognitive outcomes in very preterm infants, but too heterogeneous, more research needed. Be careful of what you read in a structured review or systematic review where that's possible, because this is one done by, you might spot Gorm Grice, and he was in the, I described as one of the really senior people. His lab's done the same thing, came to significantly different conclusions to our systematic review, but leaving that aside, it's just a general comment. Here's another one that we did from my lab, again, a different group, not preterm, but with hypoxic ischemic encephalopathy. This is the group who particularly are likely to have seizures. And really what the literature says is some of those patterns, burst suppression, low voltage, flat trace, reasonably accurately predict long-term neurodevelopmental outcome. Not, reasonably accurate being the term. And, on average, we probably didn't need an EEG to predict, because if you have a flat EEG, you look pretty flat, and we've known for a long time that an outcome is likely to be adverse. But that's the state of the art. People have sort of tried to develop areas of using these sorts of observations along with clinical information, and talked about risk factor models, so a whole kind of developing science of its own, and the predictable kind of thing. We've got big data by definition with EEG. It goes on for as long as you record it. The arrival of machine learning, and all of this needs to be viewed in the context of an evolving individual brain. So people are trying to do sort of smarter things. But I'll just end with the point that if you just do a PubMed search around EEG in the newborn, the first one was done back in 1937 in children, in babies. So it's taken 8,000, sort of all those years to get to 8,000 references. MRI started a lot later, 45 years, I think I calculated, but it's already outpacing EEG in terms of what broadly might be worth researching. So look, to answer the question, which I did at the meeting, are we missing important prognostic information? Probably not. It's been done to death. It's a bad test or a bad presentation of a signal. So why keep banging away at something that we can do better at? And that's really, does EEG, however, have the potential to provide really accurate, individualised prognostic information and real-time biomarkers of stereotypical and aberrant neurodevelopment that would allow us to assess the efficacy of interventions for their neurodevelopmental disorder at the time? And that's where the answer to that is yes. And that's where James Roberts, heading up the lab in cognitive neuroscience at QMRB, comes in, along with his lab. I notice one of his postdocs in the room as well. So James, that was really the starting point. We've had NHMRC funding, we've got MRFF funding for cohorts of high-risk babies where we are collecting EEG and MRI, but unless we're doing something better than some visual inspection like AEG, we're sunk. So over to you, James, to tell us the way forward. Thanks.
Thanks, Paul. Just need to... I've maybe broken screen sharing. Should we all good on Zoom? Somebody yell out if not. So hi, yeah, I'm James Roberts at QIR. Thanks for the intro with Jason and Paul. So yeah, Paul asked me to sort of give some ways forward, some ways to go beyond what's been done traditionally. So we have a few sort of angles that we're pursuing here, and one of them is to automate analysis of EEG, which Paul mentioned a bit of. So it's kind of silly that humans eyeball these things. I think humans clearly didn't evolve to eyeball squiggly lines, especially ones that are sampled at hundreds of hertz. And So EEG specifically, not so much AEG, is basically the best possible thing we have for practically measuring brain function in infants. But the problem is that it's very difficult to interpret, hence AEG being this sort of simplified measure. And that's particularly a problem in the clinic where at, say, smaller hospitals and things, you don't have this expertise. And even in a big hospital, that expertise isn't always there. So hence, that's where machine learning and AI can come in to try and automate some of this interpretation. So you don't need to have the expert. So we, particularly Nathan, have a whole suite of these algorithms now in play. So things like seizure detection. So instead of having a neurologist eyeball these things sometime later, you can have software say seizures happening now. We have sleep state detectors, HAE classification of the background, like Paul was mentioning, detection for things like hemorrhages. We have measures that pull out things that are not easily eyeballed using methods from physics to find information that is just buried under the surface. Also, artifact detectors. Say you want to actually build a system to do this. Sense an alarm off. You don't want the alarm going off all the time just because the baby was wiggling. Say, so you need. There's a whole suite of algorithms that can go into a pipeline to hopefully augment care in the clinic. So things like preterm outcome prediction. Another Paul also mentioned. The most recent one we've been doing is kind of moving beyond some of the classic signal processing things to try and get us something more biological and capture the sorts of things that are done in pediatrics routinely anyway, and that's to have like a growth chart for brain function. So there's one of the things that somebody reading an EEG might do is say, ask, is this correct for age? Just like you take a baby, it gets weighed, they say, oh, the baby's weight's looking good, put on a growth chart. So the idea is to apply the same kind of idea to, is the baby's activity going correct for age? So for instance, if we do this and it uses numerous features from the EEG, some of them are ones that the clinicians look at, some of them are ones that you can't really eyeball and you need signal processing to do. It works really well. Like you can get, to within a week accuracy, even less. And because this brain age idea is used, or it's kind of popular now, especially at the other end of the lifespan for neurodegeneration, for people being old for their age. But babies develop so quickly that it's actually a really sharp measure at the start of life. And that cloud of dots isn't just a cloud. Babies actually, if you track the same baby, they follow well-behaved trajectories. And the neat thing is the algorithm is already at the level where it outperforms human experts eyeballing EEG and saying, oh, does this, estimating the age and comparing it to the actual age. And interestingly, in that middle column on the bottom, human experts looking at AEG even seem to be systematically biased and underestimate the age. As our FBA stands for functional brain age. So our algorithm is, less biased, more accurate. And Nathan's has an ideas grant following this up to older ages throughout, up to adolescence. And the other thing we are trying to do currently, setting up and going through lots of paperwork and fun, is to try and start getting these into the clinic at Royal Brisbane by running algorithms either on existing hardware that we can access, and also developing our own hardware. And we want to be able to show that, just a dry run initially, that look, had we used this algorithm, this would outperform, or at least not underperform compared to a human expert. And then hopefully this will lay a platform for future trials where we actually try and start involving the test that the algorithm can actually improve care and improve outcomes. So a long pathway ahead of us here. So on another topic, which is really moving beyond what AEG can do, and that's treating EEG more like it's done in the adult space, where you have multiple electrodes instead of just two, where it really becomes a form of neuroimaging. So you actually have spatial information in there. So EEG is never going to be as spatially precise as MRI, say, and certainly not as precise as all the methods you can use in animals. but it has good temporal resolution, and the spatial resolution is good enough to be able to access some of the richer information that's happening underneath. And there's another comment on that MRI point. It's it's actually used quite a bit currently, it seems, but it's really for babies, but it's tricky because the fMRI is this very indirect measure of brain activity, but basically dependent on how the changes in blood oxygenation relate to brain activity. And in adults, that relationship is kind of well behaved. In babies, it's not so well behaved. So it's kind of questionable how much you're measuring brain stuff versus blood stuff. And also in practical terms, it's just not very available in a lot of hospitals. And it's a big hassle to move a baby to an MRI machine. So, but a lot of the tools that are developed out in adult fMRI land can also be applied in EEG land. So one of them is looking at functional connectivity, which I always think is kind of a silly term, because really it just means correlations between pairs of regions. So if you have the activity in two different parts of the brain, you can see how correlated they are. And if you do this for all the different pairs, you kind of build a network. And that's something that's really getting at how is brain activity organized across the brain? How does it all talk together? And that's something that's inherently multidimensional, and that's a really hard thing to eyeball. So it's really going beyond what you can just see in an EEG trace. And so that basic idea is kind of the heart of the relatively new field of connectomics, right? Where you're looking at networks. So I didn't actually realize that all the screens, you guys can't see this. Yes, sorry. I thought it was just on my screen. Sorry. So, a lot of the connectomics energy is put into looking at psychiatric disorders, all these more subtle disorders, right? AEG, something is kind of can see really, where something really bad has happened. Like Paul said, if the EEG is completely flat, something bad has happened. There's probably a lesion or some major injury, and lots of neurological disorders. Things like epilepsy are really easily seen with simple measures by eye. But almost all of psychiatry, learning difficulties, all the more subtle stuff, it's thought that these are all sort of subtle disturbances of networks. So just to illustrate the sorts of things you can do, we've, with our collaborators in Helsinki, looked at EEG from term babies measured near term and preterm babies measured at term, with enough channels that you can start to do what's called source reconstruction and work out where in the brain was the activity happening. And then we also in particular looked at the two main sleep states in a baby. So it's called active sleep and quiet sleep. So it's kind of like in adults, we have REM sleep and non-REM sleep. So the way it kind of proceeds is you do your source reconstruction to work out where all the activity is at all the different regions of the brain. And then you do various processing to work out, how does the activity in these regions all correlated. So you get these connectivity matrices. And then there's various statistical methods you can use, one called the network-based statistic, for instance, that lets you identify, okay, if I compare my active sleep to quiet sleep or my preterm to term, which connections seem to be significantly different between them. So for instance, if we do this between sleep states, you can see that there's these huge range of long-range connections that are stronger in quiet sleep. So that's the blue edges in that graph. And then there's this sort of shorter distance network in the occipital region. So it's like visual cortex that's higher in active sleep, which is kind of interesting to think of from the perspective that, if active sleep, like REM sleep, is like when dreams are happening, then there's visual stuff happening. That's kind of a neat thing to fall out. So if you compare preterm to term, seem to be, a whole bunch of long-range connections that seem to be upregulated in the preterms. The really interesting thing is this, like the sleep by group interaction. So like comparing active sleep to quiet sleep in the controls versus preterms, specifically for that, that occipital network, that visual one. So there we find in the controls, there's a kind of big reorganization between active sleep and quiet sleep. And that seems to be attenuated in the preterms. So there seems to be, you know, this sleep-wake cycling is actually one of the things that clinicians look at to see that, oh yes, this baby's progressing well. So it's kind of neat that that seems to come out in a network case. And it also seems to correlate with visual performance at 2 years. So that's still not yet at the sort of level where you could, you know, get that into the clinic and, you know, make biomarkers and stuff. It's kind of an interesting, a nice lead here. And that was work led by Anton Tokariev in Helsinki, who's gone and done a whole bunch of these network analyses since. Which brings us just finally to what Paul mentioned, large cohorts. So we want to do more of this with much bigger samples. And so Ros Boyd at UQ and many other people, including Paul, recently received an HMRC Synergy grant. It's going to collect hundreds of at-risk babies across 3 sites, Royal Brisbane, Monash and Westmead. So various at-risk groups. So it's at risk for cerebral palsy principally, but a whole range of neurodevelopmental poor outcomes. So they'll be extremely and very preterms, mid to late preterms, small for gestational age, and also HIE and stroke, as well as healthy controls. And the nice thing about this cohort is that they're going to have early, like for the preterms, they'll have one at sort of 32 weeks, MRI and EEG, and then again at term, and all the babies have all these at term. And they're very richly phenotyped. There's going to be heaps of other data collected. There'll be genomics, there'll be gut biome. There's the hope that we can look at, you know, gut-brain axis type stuff, and then lots of follow-up, a huge battery of follow-up tests. And, you know, the overarching aim is to find early biomarkers for neurodevelopmental outcome, where we'll use, some of us will be looking at MRI things, looking at networks in sort of structural, how's the white matter connected, and also functional, and do the same in EEG. And then we can also relate these to find, you know, are there abnormalities in the structure that relate to function and vice versa. And, you know, there's a hope here, particularly because this cohort has a lot of the milder, sort of lower risk cases. So where, you know, they're not as at risk of seizures, say, but there are at risk of poor outcomes that are more subtle. So the hope is that with access to all this networks information, we can start getting at some of the, you know, the subtle early seeds of, you know, psychiatric illness. You know, maybe we can find early markers for ADHD or something like this. So that's kind of the hope. And recruitment begins soon, so hopefully there'll be more to talk about on this soon. So I think we started late. I should just throw the summary up now and say thanks.
James, can I ask a question about understanding it closer so that the people online here, about the data that you have available to you analysing? Are there any new technologies which are emerging to measure brain activity, etc., which you could also incorporate in a multimodal sense to increase the accuracy of what you're trying to measure as well?
So I think the big new thing that, well, one of them is like, it's called FNIRS. So it's not super new anymore, but there is this hope that it is something that's sufficiently non-invasive, unless you do MRI type stuff on the scalp, essentially, without having to go all the way to a scanner. And there's also hope that similarly magnetic encephalography, magnetic encephalography, which is usually another one that is very expensive, very complicated, but there's attempts now to have smaller ones that can be used and get better spatial activity, spatial resolution. Otherwise, the hope is all the other autonomic measuring, use all the others, all these other things that are measured as well. like things like heart rate variability relates to all sorts of things, respiration, SpO2, just more data fusion across all the other things that, change with the brain activity, but not a direct measure of the brain.
Not to forget, it's about fusion of data, but also more convenient methods. And I guess we should all be aware that Perth is receiving a very low field strength MRI. So I think it's 0.1 Tesla, but I'll stand corrected, which means that you can wheel a big ultrasound sized machine right up to the patient in the nursery. So we've already been tapped on the shoulder to say, what could we do about this? But of course, inherently losing signal, but with sort of comparative with 3T data, the whole AI approach to trying to generate meaning from this new, easier technique is there. So plug for her.
Actually, thanks for talking. And I got a question about one figure. It's actually, I remember there is a figure show that the EEG can be used to predict the age, right? And there is a linear relationship between the age and the age. I'm just wondering if this can be used for that.
So used for what?
For
For adults. Oh, yes. So yeah, the question was, can this brain age idea be used for adults? And then, yeah, absolutely. So
it's also a relationship, the linear relationship between the adult age and
the age estimated. Yeah, I mean, it's kind of expected for a healthy, I guess you'd expect for a healthy brain, it should be linear. For healthy people, your brain age should tick along at the same age as your chronological, the same time rate as your chronological age. But the argument is, say, if you're older and you're in neurodegeneration, say, then maybe you start to fall off the curve. So you may no longer have a linear relationship.
because, the reason I ask this question is because my background is forensic medicine, and there is a subject called forensic anthropologist, which is focused on especially it is very important for us to identify the criminal's age, and sometimes we use the born, the X-ray, like this kind of things to identify the age, but usually this kind of method is reliable. But I mean, if this is also reliable, it can be used as a new method to identify the criminal's age. Very interesting.
Yeah, we'll have to be alive though, right? That's the tricky bit for forensics, I guess. But, yeah. Thanks.
That's great, James. Thanks very much. So we're fortunate enough to have Mitchell McMaster present next. Before we get underway, I'm very sorry, everyone. I forgot to give the acknowledgement of country in my haste and excitement for the presentation. So I'd just like to acknowledge the traditional custodians of the lands on which we meet and pay my respects to elders past, present and emerging. But it's great to have Mitchell present to us. Mitchell is going to present to us on cognitive decline, a window of opportunity for reducing the risk of dementia. Mitchell has a background in neuroscience and psychology, and his primary areas of research are maximising the quality of life in people living with dementia and reducing the risk of dementia. He's very well credentialed to give this presentation. And so, Mitch, when you're ready, feel free to share your screen and get underway.
Thank you. All right. Share. All right. So thank you for inviting me here to speak today. This is actually the first presentation I've been giving since officially becoming Dr. McMaster. So it seems only fitting that I present on my PhD today. So just a bit of an overview. First, I'll give some background, speak a little bit about cognitive decline, then the methodology I used in the study, and then I'll cover some of the major findings, so the primary outcomes, a little bit of the feasibility, and then summarise it all and talk about some future directions for the research. So we'd all be familiar with the increase in the number of people developing dementia with the world's ageing population. What's less well known is that lifestyle accounts for 40 to 50% of dementia risk. And separate to this is lifestyle, which is one of the strongest risk factors for cognitive decline. So for anyone who isn't familiar with the terms SCD and MCI, for subjective cognitive decline, as the name suggests, these people score at normal levels and normal cognitive levels, but subjectively they can notice they have declined from what they used to be. With mild cognitive impairment, there are measurable impairments in cognition from what you would expect, but these aren't significant enough to meet the levels to be classified with dementia. And there is some debate about whether these conditions do precede dementia, but they are definite risk factors. And with these individuals, we can see low levels of the same neuropathology we see in Alzheimer's disease, so things like amyloid plaques and tau tangles, atrophy in structural neuroimaging, and abnormalities in functional neuroimaging as well. And these conditions generally have a wavering time course, so they may improve or they may decline over the short term. But over the course of a year, a minority of people with these conditions will remit back to normal cognition. So for MCI, this is around 30% per year. But if you look at these conditions over a longer period, they do generally decline. So for SCD, over 7 years, about half will progress on to develop MCI. So they'll go from having the subjective deficits to objective deficits with MCI. And with MCI over 6 years, about 60% develop dementia. So they move from having these objective deficits to actually meeting the criteria for dementia. So the hypothesis for the PhD was that with these conditions, these conditions can sometimes remit without any intervention, may indicate that the brain retains sufficient neuroplasticity at this stage that with the right intervention, you may be able to modify the trajectory of the decline. So given that there's a few years of this wavering time course, this may present a window of opportunity where we can successfully intervene. And for this study, we're looking at to reduce lifestyle risk for dementia and increase cognition. And systematic reviews have identified this cognitive decline period as under-researched, and lifestyle interventions in this group similarly under-researched. So for the PhD study, I took a previously successful dementia risk reduction intervention, and I adapted this, that was for cognitively normal but high risk people, so high levels of lifestyle risk, and adapted to people experiencing cognitive decline, and incorporate aspects of other different successful interventions as well. So it was an 8-week RCT. Participants were stratified by gender, the 2 primary outcome measures, so lifestyle risk for dementia and cognition. And we tested them at baseline, immediately post-intervention, so week 9, and 3 months post and 6 months post. And for cognition, we only tested them at baseline, 3 and 6 month follow-ups. So the interventions themselves, so for the active control group, they took part in 4 educational modules, so on dementia and risk factors, and how to implement the Mediterranean diet in their own lifestyle. The levels of physical activity that are recommended to reduce dementia risk, and also the sorts of cognitive engagement that research indicates may be beneficial. And we instructed the participants to implement these into their own lifestyles. So with the intervention group, they completed the same modules, but in addition to that, they had an appointment with a dietitian to help them implement the Mediterranean diet, appointments with exercise physiologists to set up an exercise plan with the eventual aim of building that up to 2.5 hours moderate exercise per week, and also cognitive engagement using the Brain HQ platform. which is similar to lumosity, if you know lumosity, but there's a bit more research backing for Brain HQ. So just looking at the flow chart. So we started initially with 119 participants, and by final follow-up, we had 48 participants in each arm. So with the intervention group, close to 85% retention, so that's pretty good. Just a note about the analysis I used. So the analyses were linear mixed models. The fixed effects were group, so it's the difference between the intervention and control group. Time point, so the difference along the course of the intervention, and the group by time point interaction, so difference between groups over the course of the interaction, over the course of the intervention rather. And the interaction term is the main determinant of whether the intervention's been effective. So the random effects we used were gender, lifestyle risk, and cognition. Just get that out of the way. Cognition, and we stratified by the individual. Which we stratified by, participants were stratified by lifestyle and cognition, and we used individual as an additional random effect. So with significance, we determined this using the likelihood ratio test. So that's essentially an N over for the equation with and without the effect of interest. So in this case, we were using group by time point. So the equation at the top of the screen, you'll see the fixed effects are group, time point, group by time point, with plus the additional effects of random effects, gender, lifestyle, cognition, and individuals. So it'd be that divided by the same thing with the group by time point interaction taken out. So if that's thrown you off a little bit, don't have to worry too much about that. Just know that the main thing we're looking at is the magnitude of group by time point interaction, and they'll be presented as a chi-square. All right, so just an explanation of how I'll present the results as well. So blue lines will always be the intervention group, and the red lines will always be the control group. And I've inserted small arrows to the right of the graph, which just show the direction of an improvement. So just as some example data on the left, we have adherence to Mediterranean diet, with higher scores showing greater adherence to the diet. And on the right, we have lifestyle risk associated with cognitive engagement. So in that case, lower scores indicate lower risk. So just look for the arrows to see which way the improvement. And I mentioned on the last slide, the main determinant of efficacy is the group by time point interaction. So all the chi-square statistics that I've included are for the interaction term. And that's the main determinant of the effectiveness. And on the graphs, the significant stars are for t-tests between groups. That's more of a secondary outcome, which shows the magnitude of differences rather than whether there was an overall effect or not. All right, so just moving on to the findings. So the primary outcome for the study were lifestyle risk for dementia, which was measured by the ANU Alzheimer's Disease Risk Index, so the ADRI, bit of a mouthful. And that's based on 15 risk and protective factors. The strength of these was determined based on pooled effect sizes from a range of systematic reviews. For cognition, I used the ADAS-Cog Plus battery, which uses 5 cognitive measures. They're designed to be sensitive to the early stages of cognitive decline. And these 5 measures were converted to Z scores and then averaged to give a global cognitive composite. And here are the primary outcomes. So on the left, we have lifestyle risk for the groups over time. For the intervention group, it's initially pretty stable and improves and then remains at lower levels of risk. The control group gets worse and ends up slightly improved from the baseline levels. For the ADRI, a change of 2 or more points is considered clinically significant. So you can see the intervention group drop from about 10 to about 7.5. On the right, we have the cognitive composite. Sorry. And for the intervention group, we just see a steady improvement over time, and the control group gets worse and then returns to baseline levels. Both had significant group by time point interactions, so the intervention was successful. So looking more specifically at risk, we broke this down into risk and protective factors. So for risk factors on the left, pretty stable for both groups, no significant interaction term, but we can see all the improvements were made in the increased protective factors on the graph on the right. So for the intervention group, the risk levels decline and then drop off even further and remain low, whereas the control group gets a little worse and then improve to be only marginally improved at the final time point. For the intervention group at baseline, it's around -8.7 and declines to -11. So again, it's clinically significant outcome. So here we have the 5 cognitive measures that were combined to make the cognitive composite. So you'll see over the bottom right, we only had one significant interaction effect for SDMT, which is a processing speed measure, which is the graph on the top right. So when we saw these, we were a little bit puzzled. You'll recall from the cognitive composite score, the intervention group had a consistent upward slope, and the control group declined and then returned to baseline levels. And the differences between groups at both time points were significant. Whereas here, the results at first glance look quite a bit less impressive. But if you do look a little more closely, what you actually see is that the intervention group improved on every single outcome, whereas we can only say the same for 2 of the outcomes for the control group. So the way we interpreted this was that there was a consistent weak positive effect across all measures, so that when were combined, we see that consistent cognitive composite score. So just to recap, the intervention group were able to show statistically significant and clinically significant improvement in lifestyle risk, as well as a statistically significant improvement in global cognition. And so what demonstrated this effect quite clearly was the control group weren't able to modify their lifestyle, and subsequently there was no difference in cognition either. And this contrasted quite well with the intervention group. So those results were published in 2020, and I was hoping there would be some media engagement with them. And it was a lot more popular than I anticipated. So I ended up doing 7 radio interviews, 2 newspaper interviews, and I appeared on the ABC Midday News as well. So amazing coverage. And it was also quite popular on social media as well. Ended up getting an altmetric score of 336, and it's been cited about 30 times since 2020. So just talking a little bit about the feasibility. So feasibility studies are usually done in preparation for a formal RCT to determine if the study should be run, and if so, how. So usually in the form of a pilot, but they can also be run post hoc, as was done with this study. And it's a good way to look at what aspects worked and what didn't work, so that you can maximize the outcome in future studies. So we looked at retention, so measured as a percentage of participants who completed the intervention. Compliance, so this is how well participants actually did what we asked of them. Did they comply? And adherence, how well were they able to lower their lifestyle risk? So retention was measured at immediate follow-up. So more than 85 participants completed the intervention, so it does demonstrate acceptability. Compliance was also quite strong for those who stayed in the intervention, 100% compliance on the online modules, the Mediterranean diet, physical intervention. There was a lot less compliance with the cognitive engagement. So we didn't formally collect qualitative data on this, unfortunately, but the feedback was that completing 2 hours of training every week on only 4 cognitive tasks was a bit laborious. So there's quite a spread of compliance. Some completed exactly what we asked, others quite a lot less, so quite a spread there. So here we have the adherence. So this is how well participants were able to change their lifestyle in the 3 domains of interest. So the top left is Mediterranean diet. So both groups did improve and then plateau off, but we see a much stronger response for the intervention group. So they had the assistance of the dietitian to help implement the Mediterranean diet. And you'll see there was a significant LRT score for Mediterranean diet down the bottom right. On the top right, we have cognitive engagement. So in spite of the low compliance, the intervention participants were doing enough to lower their lifestyle risk. And again, a significant interaction score. Less positive outcomes for physical activity, looking at changes from baseline to final follow-up, very little change for either group, and accordingly, a non-significant interaction score. So just to summarise that, there were high levels of participant retention. Compliance was mostly high, with the exception of the cognitive engagement, and adherence was similar, quite high, with the exception of physical activity. So bring it all together, the intervention was able to demonstrate efficacy to reduce lifestyle risk of AD and improve cognition. And the intervention was feasible, but there were clearly some areas that could be tweaked. And bringing the findings of the two papers together, the evidence clearly favours the more intensive individualised interventions rather than passive education, where people are required to implement the changes in their own lives. And that's probably especially true for a group experiencing cognitive decline. So looking at the directions for future research, the results do support a larger, longer study. And so having a larger study, of course, enables better power to demonstrate benefits for measures with smaller effect sizes and the different, so thinking of the different domains of cognition and also health-related quality of life, which I wasn't able to speak about today. Systematic reviews on these interventions have recommended lengths of 2 or more years to fully demonstrate the effects and also demonstrate the longevity of any outcomes as well. So in terms of the intervention, for lifestyle, we saw that there were significant effects for increases in protective lifestyle factors, but no effects for decreasing the risk factors. So definitely some scope for improvements there. However, this is a finding that's been seen across other studies as well. So while the intervention was overall feasible, there were some low levels of compliance with the cognitive engagement and adherence for the physical activity intervention. So definitely some tweaks that can be made there. In terms of other outcomes we could have included, we did only have objective measures of cognition, which are important, of course, but with SCD, the cognitive complaint is subjective. So a subjective measure of cognition tells us whether the participants are actually noticing a difference through taking part in their day-to-day life. Neuroimaging measures would also be interesting. So if we could replicate the cognitive outcomes, would we see a decline in the rates of atrophy in some of the areas? Would we see, in areas such as the entorhinal cortex and the hippocampus, we see reductions in the rates of buildup of amyloid and tau, and would we see any functional improvements? Be quite interesting to look at. There's not much being done in that area. Similarly, with other biomarkers, would we see any changes in CSF or blood-borne biomarkers? And those are largely unexplored, but critical to show that these interventions have some real benefits to the underlying pathology. So just some acknowledgements. My PhD was funded by Dementia Australia Research Foundation, ANU, some additional funds from some other partners, and also the participants for their time and effort and my research collaborators. Thanks.
Thanks very much, Mitchell. There's some applause going on here in the auditorium, as I'm sure there is in virtual land. Can I ask if anyone has any questions for Mitchell? Just to be a brief question. Just while people are thinking about an additional question, I just want to ask Mitchell about longer term studies, which you identified as something which would be a useful follow-on from the work you presented. Have similar interventions or approaches been subject to longer studies in the past? And in those studies, if that is the case, have some of the initial gains continued, or do they, in previous studies, have they sort of returned to baseline?
Yeah, so These sort of interventions, I guess, are in their infancy. There haven't been a lot run. There was one large study called the Finger Study, which was run in Norway, and it was run for 2 years. I think it was around 2015. So now they're starting to look at some longer term data. So yeah, there are other studies, not in this field specifically, where you get the decay of the improvements. So one of the things people are looking at is whether you need boosters to ensure that people's lifestyle is improving and increase that longevity. So the only studies that have been done for 10 years or more are in the cognitive engagement. And there was one study which had boosters, and people were showing decreased levels of dementia after 10 years. But these multi-domain studies are quite newer, and not as many have that long-term. Oh, very few. I don't think I've seen any with what you call long-term data.
That's great. Thank you very much. We've got one question in the auditorium.
Yeah, thanks, Mitchell. Very interesting. Paul Colditz here. The stimulus for my question was looking at the variance in the error bars on your mean data points was the way I understood it. And of course, like all biological data, it looked wide to me, not quite knowing what it exactly was. And this has got some cost associated with it, just a bit of rough arithmetic, 1 hour in your control group versus 8 hours in your intervention group. If you put your cost benefit lens on sort of maximum power, there's an opportunity, I think, there to try and identify who are the responders and who are the non-responders that underpin the variance in your results. And is there an opportunity to kind of somehow identify the people who are the big responders, the rapid responders? Thanks.
Yeah, definitely. So unfortunately, we weren't able to do qualitative to look at, why were people low with compliance or low with adherence. But yeah, it's definitely something we could look at in future studies. In terms of maximising that bang for buck, so improving people, helping people that aren't hitting that real compliance and adherence, getting benefits for them, for the ones that aren't as well. So.
Well done, Dr. McMaster. We're very happy for you and your PhD graduation, and us being such a priority on your list of groups to present to. It was certainly a pleasure for us, just as it was for Associate Professor Roberts and Professor Colditz as well. So thank you everyone for attending the seminar series. We look forward to the next meeting. Thank you.